Alright, this is chapter 19. This is going to be part 1, which is the, we're going to talk about different types of reactions. And so part 1 is going to just talk about a couple of the types of reactions. And then we'll go and do part 2, which is going to talk about a couple more different types of reactions. And so, the screen's being silly, so just hold on a second. Maybe. Okay, here we go. Alright, so a couple things we need to review before we start writing reactions. The first thing we need to review is something called diatomic molecules. Diatomic molecules are our two atom molecules. Okay, and what they are is I will commonly refer to them as the magic 7. Remember that they start at 7, meaning they start at nitrogen. They make a 7, and that there are 7 of them. And I put a list of them, of course, in your notes as well, just to remind you what they are. What these are is that when you go to write a reaction, like for example, let's say I want to write what happens when you make water. So, you know, you're going to take hydrogen and you're going to add oxygen, and that's going to produce, you know, water. The thing is that you would never see this, where you would never see just H and you would never see just O. There are certain elements that never exist by themselves. They always exist as twins when they are not placed with another different type of element. Meaning that when hydrogen is not placed with some other element, meaning like if it's not in combination with oxygen, it always exists with a little 2 after it. There's always 2 of them. Same thing with oxygen. It always exists as a 2. So these 7 elements you would never see written as just nitrogen or just oxygen. It always would be N2 or O2 if it is existing outside of a compound, meaning by itself. So that's something that you want to make sure that you are aware of, and that when we write reactions that you do, because if not, it's going to be really hard to balance your reactions. The other thing I want to point out is that this information about if you're looking at a reaction or you're getting ready to write a reaction, you're going to put, after the reaction, you're going to put little S's for solids. You're going to put a little cursive L after it for liquids. We don't use a regular L, like just, I guess a lowercase l, because it looks a lot like a 1. So we use kind of a cursive L. A little G after it for gas. And AQ, aqueous, dissolved in water, meaning that that particular compound is just free-floating ions. So, for example, what I'm talking about here is that you might see like sodium, for example, with a little S after it. Just kind of almost like you would do your little subscripts when you crossed your charges. The difference is, of course, that these are in parentheses. Okay? Alright, so let's talk about some types of reactions here. So the first part of this is we're going to talk about synthesis, we're going to talk about decomposition, and we're going to talk about single replacement. First up is synthesis. If you synthesize something, that usually means that you make something, you form something new, and that's what happens here. 2 substances basically combine together to form a new substance. Originally, these were also called combination reactions, because that's what they did. They combine things together. Here in the case, and keep in mind, we're doing very basic reactions. We're not getting into the nitty-gritty. We're not getting into the more complicated stuff that you're going to learn later on if you decide to take a full year chemistry class. Here in the sense that what we're going to do is we're going to take an element, we're going to add it to another element, and we're going to get a compound. And that's what they're showing here with this example. You have element A, you're adding it to element B, and guess what? You're getting a whole new compound, element AB. Alright, so let's look at some examples of how you're going to use that. So let's say that the compound starts with a sodium. Okay, so for example, it's sodium, so you have a metal here. Actually, I'm going to write that at the bottom, sorry. Alright, so you have a metal here. Okay, and that metal is, in this case, sodium. Now, one thing you need to do is you're writing these along, going, okay, well, sodium, is it a metal or a non-metal? In this case, sodium is a metal. And then you have to ask yourself, alright, is sodium part of that magic 7? Well, no. So it doesn't need a 2. You're just going to put a little subscript after it. It's added to some oxygen. Last time I checked, oxygen is a letter O. And then you have to ask yourself, okay, oxygen, is it part of the magic 7? Yes. So it gets a 2. The gas. Okay. Now the key, the reason I asked if it was metal is because that tells you you're going to do just like we did with our formula. And you're going to use the charges. Meaning that I'm going to come up here in my free space. Sodium makes a 1 plus charge. Oxygen makes a 2 minus charge. Cross them. The product that you produced is Na2O. Now, you have a chart in your little arsenal that I handed out. And it's called a solubility chart. The solubility chart gives you an indication of what is soluble and what is insoluble, meaning that what's going to turn out to be solid and what's going to turn out to be aqueous when you do a reaction. So you're going to take your finger and you're going to go from sodium and you're going to go from oxygen, bring your fingers together, and you should find out that this compound here is aqueous. So you're noticing the things you're having to do. First of all, you're writing everything in forms of symbols. Then you're going to have to go and put the, if they're solid, aqueous, or gas after them. And then, of course, the last thing you have to do with this equation is you're going to have to balance it. So in this case, I'm going to have to put a 2 here. I'm going to have to put a 4 here. And I think that's good. Well, we need the 1 there. So, and of course I did that really fast because we all know how to balance, so there you go. Alright, so there's the example of the one with the metal. Let's talk about what happens if you have here a non-metal. Like carbon. Excuse me. Carbon, so they're telling you it's a solid. And again, it's not part of the magic 7, so it doesn't need a 2. Oxygen, however, is part of the magic 7, so it needs a 2. What's going to happen here, now keep in mind, non-metals, if it starts with non-metals, no charges. Okay, just combine them together. CO2. Okay, now the last one. So basically, you're just going to put them together. Easy enough. Just put whatever it is there, whatever it is there, and put it together. Last but not least, what we're going to talk about just here real quick to clarify. Iron, which is a metal. So Fe with a solid. It's not part of the magic 7. Sulfur, which is a solid. Again, not part of the magic 7. What do you do if that first metal is something that you don't know the charge of? Well, I will always, for right now, obviously give you the charge of that metal. So in this case, you have Fe, which is a 2 plus, sulfur 2 minus, FeS. Okay, so, and obviously I didn't balance the last one, but it's all 1s. This one here, again, this one works out to be all 1s. Okay. Oh, and I didn't look up the solid, liquid, or gas for FeS. FeS would be, let's see, that's iron 2. sulfide is a solid. Okay? So there's your combination reactions or synthesis reactions. Now we're going to talk about decomposition reactions. Okay. Decomposition reactions are just the opposite of synthesis reactions. Okay, so think about what decomp is. It breaks down. If something's decomposing, it's breaking down into its original form. So it's exactly what these types of reactions do. So for example, you have that compound now. It's breaking down into element plus element. These require a lot of electricity or heat or light in order to make it so that these happen. Okay, so let's look at some examples of these. Alright, so they give you mercury 2 oxide. Okay, so we know the mercury 2 oxide is, and we can put some think process up here if we need to. Oh. Hg. So 2 plus, oxygen makes 2 minus, so mercury 2 oxide is HgO. So what's going to happen next? It's going to break down into its elements of Hg and O. And then, of course, you're going to make sure and check, do any of those make the magic 7? Yes. Now, typically you would look up and see if these are solid, liquids, or gases, but we don't have periodic tables that are labeled as far as that goes, so I'm not going to be picky about that. So we'll just leave it as it is. Of course, make sure you balance your equations. In this case, 2, 2, 1. Okay. Alright. Same thing, the next one. So you have silver 1 oxide. Silver 1 oxide is Ag 2O. Okay. So this one is going to break down into Ag plus O2. And again, you want to make sure that you balance your equations. And there you go. Then you have like water. And hydrogen is a diatomic, so make sure you put that 2 with it. And same thing with O. Alright. And then last one, sodium chloride. Na. And then chlorine is a diatomic, so there you go. And I didn't balance those last two. So let's see, you need 2 there, 4 there, 1, and 2 there, 2 there, 1. Okay? So there are your examples of your decomposition reactions. Okay? Sorry if there's a pause here. The screen's taking a minute. Okay, so next, last but not least of the types of reactions in this first part of the video are single replacement reactions. So this is where you have a reaction, and you'll see here in the example here. So this is where you have, what happens here is you have an element and you have a compound. And what happens is, I'm actually going to erase this now. What happens is that an element here comes in and replaces another element in the compound. It's like they switch places. So look here what happens. All that happened here is that A and B switch places. Think of this as like dating, okay? Somebody's in a relationship and they decide that they no longer want to be in a relationship, so they go and date somebody different. Okay? So they're dating somebody. So A is dating C. They decide no longer they want to be with C. So now they're going to go, I guess we could say that, kind of rephrase that. C is dating A. C no longer wants to be with A, so they break up. So now C and A are together, and it's with B. If that kind of makes sense. Probably not, but you kind of get the point. Okay? Now, here's the thing though. Elements, there is a chart over here to the right hand side, and you actually have a separate chart. So, and I think of it as the hotness chart of elements. So, how hot an element is, meaning that will an element replace another element? And in fact, we need to add one thing to this chart right in here. You need to add hydrogen, because that was left off. Okay, in between lead and copper. Okay, so here's the thing. We could kind of again think about this with relationships. If two people are dating, and they're not probably going to break up, and somebody's going to go with somebody else if that person is not better. Like you're not going to break up with somebody and go with somebody worse. So you're probably going to stay with who you are with. You're going to go with somebody who's better. So that's what the element, this whole chart is about. Like for example, okay, let's take manganese here. Manganese is like right here on the chart. Iron is down here on the chart. Manganese is higher on the chart. So if somebody was dating, let's say, iron, right? They would break up with iron to go with manganese because manganese is higher on the chart. However, let's look at this situation in reverse. Okay? Let's talk about two different elements now. Okay? Let's say that somebody was dating, I don't know. Let's say somebody was dating potassium. Okay? They think potassium is the bomb. And they're looking into gold. Okay? Would they go back down the chart to go date gold? No, you never go down the chart. So this would not happen. Okay, so that's something we look at with single replacement reactions. So here we go. Let's look at some actual real examples here. So, you have iron, which last time I checked, that is Fe. You have copper 2 nitrate, which is CuNO3 2 aqueous. Now, look at this. We have iron, we have copper. So go to your chart and look. That activity series chart. Okay? And look at the positioning relative to iron and copper on the chart. If iron is higher, then iron is going to take the place. Then iron is going to take the place of copper. So basically, if Fe is here and copper is here, then iron is going to switch. If copper is here and Fe is here, then nothing's going to happen. So, if we look at the chart, hopefully you see, though, that this is true, right? Iron is higher on the chart. So that means what's going to happen here is that iron, and in this case, we're going to use iron with a 2 charge again. So, Fe with a 2 plus goes with NO3 with a 1 minus charge, because that's what a nitrate does, right? So you have Fe, NO3, 2. And again, you would look that up on your solubility chart and find out that that's aqueous. And then what happens, notice that iron came in and took copper, and kick copper out, so now all that's left is copper. Okay. Alright. Now, let's try another one. And then, of course, you would balance and all that good stuff, kind of stuff. Alright, Pb, solid, plus silver acetate, aqueous. So again, look at your chart. Lead versus silver. Okay, so I'm looking at my chart here. Finding lead. I'm finding silver. Lead is higher on my chart, so there's going to be a switch. So again, we're just going to be consistent. I'm going to just have you guys from now on use 2+ charges just so it makes it easy and I don't get 500 questions about it. So Pb with a 2+ charge is going to go with acetate, C2H3O2 with a 1- charge. I'm running out of room, so I'll just write it down here. So your product is Pb, parentheses, C2H3O2. Then you would look that up and determine if it's solid or aqueous. And then you just kick the silver out, so you would have silver as a product. So we need to look up, and lead acetate is aqueous. Alright, last two examples. You have copper plus silver nitrate, aqueous. Okay, now, so we have to compare silver and copper. So if copper is higher on the chart, then we're going to switch, which in this case it is. Okay. Now, let's because I just realized that all the examples that I didn't do a very good job with giving you any variety. So I'm going to skip the last example, and actually I'm going to reformulate this one right here. Let's say this was silver and copper 2 nitrate. Let's say they gave you this instead. Okay? So this was flipped on the chart, because I want to make sure you know what to do if it was reversed on the chart. So obviously we're trying to figure out if copper... Oh no, wait. Sorry. Okay, wait, never mind. Let's go back again. I was having a old-timer moment here. Okay, so let's go back to copper plus AgNO3. So getting myself mixed up. Okay, so we're looking up and we're saying, okay, is copper higher on the chart than silver? And copper is higher on the chart than silver, so copper is going to... Yep, I was right the first time. That's okay. Alright, we'll finish this one. Copper will take the place, so we're going to treat it like a 2, NO3, 2, and then plus silver. Alright, we'll fix the last one, so sorry. Alright. Okay, let's say... Let's do one more, and let's just say that, let's take this last example we just did, and let's actually flip it. Okay, so let's say you had AgNO3. I'm sorry. Brain click on AgNO3, and it still isn't clicking on Ag, and copper nitrate. Okay. This would be an example where silver is not higher on the chart than copper, right? Because the last one flipped, obviously, because copper was higher, but silver is not higher. So this would be an example where what you're going to write is, this is my whole point of trying to do this last slide, and it just wasn't working very well. So we'll get it done, though. What you would write on this is no reaction, showing that nothing would happen here, because it's not going to flip if, there's no reason to flip. It's already with the compound that it's going to be with. Copper's not going to switch, so it's happy. Okay? So hopefully I didn't confuse you too much on this last part, and you do some practice and you'll be fine.